we are still discussing how to compute the integral of rational functions. So this is section, let me check it, 7.4 in our textbook. What we want to do today is to introduce a general method which will allow us to compute eventually the integral of the indefinite integral of all rational functions. Now, last time I already started to explain this method. So what we have given is a rational function where px and qx are polynomials. Now, the method actually works in 3 steps. So step 1 is to check whether the given rational function is a proper rational function or improper rational function. So we look at the degree of p of x. If the degree of p of x is smaller than the degree of q of x, then okay, we have a proper rational function. Otherwise, the rational function is improper. And if the rational function is improper, what you can do is you can divide p of x by q of x using long division with rest. And so in this case, if you are not in this situation, if you have a improper rational function, you can always write it as some polynomial plus a proper rational function. So we can assume that after the first step, what we still have to integrate is a proper rational function. So otherwise, we can write f of x as some polynomial. This is not good. Let's say some polynomial plus a proper rational function. This one here is proper. Okay, and this is obtained by long division. Okay, so in the first step, if the given rational function is an improper rational function, then we write it as a polynomial plus a proper rational function. And the integral then which we want to compute is then the integral over the polynomial plus the integral over the proper rational function. So what remains to handle in the remaining steps is a proper rational function. Okay, so in step 2, so what is left is to compute the integral over this proper rational function here. So in step 2, we factorize q of x as product, or let's write q of x as product of linear polynomials such linear polynomials are polynomials of the form ax plus b, and irreducible quadratic polynomials which are of the form ax squared plus bx plus c, and b squared minus 4ac is smaller than 0. Okay, so and as I have explained already last time, it's always possible. Okay, for a polynomial, for any polynomial q of x, you can always write it as a product of such linear polynomials and quadratic and irreducible quadratic polynomials. This actually is something we would have to prove, but it's not so easy to prove. Or it's not so complicated actually, but this is not the topic of this lecture. So this you will learn in other lectures, algebra. Now, so that's the second step. In the third step, the third step now consists of, okay, we will look at this factorization of g of x, and actually we will look at which polynomials will occur in the factorization, and then we will set up f of x as a sum of so-called partial fractions. That's why this method is called the method of partial fractions. So we set up f of x as sum of terms of the form normally something a over ax plus b. So this is for all the linear polynomials, and for the irreducible quadratic polynomials we will use something like ax plus b over ax squared plus bx plus c. Okay, so but actually this step here, the third step, is not very clear at the moment, because I have to tell you according to which rules do we choose such partial fractions. Okay, so the third step, where we have to set up f of x as polynomials of as a sum of partial fractions, has to be explained in more details. And in order to explain the third step, we will look at some examples. But actually, this method allows you to compute the integral of any given rational function. Okay, so you just follow those 3 steps. So rational functions are very easy to integrate, because there is a general method how to do it. Okay, so any questions to this? I will more or less explain the third step by looking at examples. So we will look at more and more complicated examples, and I will tell you how to set up the f of x as a sum of the partial fractions. Also here for the second step, normally, you know, in some cases it's not so easy to actually to factorize q of x, but you have done this in high school for many polynomials, and we will not encounter polynomials where it's much more complicated. So normally it's quite easy for the problems which we will encounter. One way to do this here, if the polynomial is more complicated, is you search for all complex roots. And then, because q of x is a real polynomial, so you know that if a complex root occurs, then also the conjugate root occurs. And you can merge those two to a quadratic polynomial, which is irreducible. So that's how you can do this for general q of x. And searching for all roots, this is something which Maple, for instance, can do. The first case, which we are going to discuss, you are able to write q of x as a product of only linear terms. Okay, no quadratic terms occur, and all terms are different. So this is the first case. Okay, so you can write q of x as a product of linear polynomials, and all the linear polynomials occurring are different. Here, if I say different, okay, for instance, this polynomial and this polynomial are the same for me. Okay, so different here means if you have 2 polynomials and you can multiply one to get the other, okay, they are the same. Okay, so this is what I mean here by different. Now, in this case, in this situation, we will set up the problem as, okay, f of x is equal to a1 over a1x plus b1 plus and so on plus an over anx plus bn. Please switch off your handy. Okay, so in this case, you can set up the problem like this here. Okay, so for instance, if the rational function, if this is our given rational function, so our task is to compute the integral. So what we want to compute is this integral here. now we will use this method. Now, you see, as for the first step, okay, we already, so the degree of the numerator is smaller than the degree of the denominator, so we do not have to do long division here. So we have already, or in other words, we have already a proper rational function. Now, for the second step, we have to factorize this polynomial here, so x to the 3 minus x, but this is easy. You see, this is what I mean, okay? If you have a general polynomial, okay, it can be much more complicated. But for most of the problems we will encounter, it will be quite easy. So you see, in particular, that we are here in the first case. We can write this q of x is here the denominator as a product of linear terms, all of which are different. Okay, so according to this rule, we have to set up f of x, maybe I write here already, x squared plus 2x minus 1 over x to the cube minus x is equal to, okay, sum a over x plus sum b over x minus 1 plus sum c over x plus 1. Now, what we have to do is we have to find a, b, and c. Now, in order to find a, b, and c, there are different methods. One is you just multiply everything with x times x minus 1 times x plus 1. And then you have left and right. You have a polynomial. You just compare coefficient. Okay? This will give you 3 equations of the 3 unknowns, a, b, and c, and you solve the corresponding system of equations. So this is one method. But if you're in case 1, there is a much easier way to do this, because a second method would be you just choose any 3 numbers for x. Okay, you just choose 3 numbers. What you get here from this are 3 equations for the unknown a, b, c, and you solve it. Okay, this in this situation, if you're in case 1, is easier, more easier method, because you can suitably choose the numbers which you plug in for x. Okay. Now, what is a good choice of such 3 numbers? You see, in this form, if you set up the problem like this, you are not allowed to plug in, for instance, x is equal to 0, because it doesn't make any sense. So, but you can first multiply everything with x, and then plug in x is equal to 0. And this is a good choice for x, because if you multiply everything with x, you have here a, and here you have times x, and here times x. And if you plug in x is equal to 0, this will be 0, this will be 0. So a is equal to, and you can already compute it. Okay? So a good choice is, so first multiply everything with x, and then plug in x is equal to 0. So in this case, if you do this, you already get a. So what is a? So here you have minus 1 and 1. So a is 1. Now, if you want to have the b, you just use the same idea. You multiply everything with x minus 1 and plug in x is equal to 1. Then this one disappears, this one disappears. Okay, and you just have to plug in here. So b is equal to, and then you have the c left. So for c, it's the same. You multiply everything with x plus 1. You plug in x is equal to minus 1. So this guy disappears, this guy disappears. And you have 1 minus 2 minus 3 minus 2 over x plus 1 minus 1, 2. So minus 1. Okay. And so overall you get x squared plus 2x minus 1 over x minus 1, x plus 1 is equal to 1 over x plus 1 over x minus 1 minus 1 over x plus 1. Okay, and once you have written the given rational function in this form here, the integral is much more easier to compute. So the integral over f of x, which is just this here, is equal to, so the integral of this one, which is the ln of absolute value of x, plus the integral of this one, which is the ln absolute value of x minus 1, minus the integral of this one, which is the ln absolute value of x plus 1, plus a constant. Okay. You know that because I compute the integral of this here, so antiderivative is ln absolute value of x plus a constant. This is, but if you choose as domain of this function all real numbers which are not equal to 0, then this is not the most general antiderivative which I have here. So we always assume if we write something like this that f of x is considered on some interval, closed interval. Okay, so this is the first case. So if you start with a rational function which is like this here, then you have to first divide the numerator by the denominator using the usual long division. So this is x squared. So you have here x over 4 minus x squared. So what you get is x squared plus 1. Then you have here plus 1. So you have here x squared minus 1. So what you get is 2. Okay, so you can write this as x squared plus 1 plus 2 over x squared minus 1. And now you go on with this part here. Okay, so, the rest is the same, okay? But actually, if you have something like this here, you can set up the problem like I have done here. So if you have to integrate so if you have to integrate this here, so you can you observe that x squared minus 1 is again a product of two different linear polynomials. So you can set up our problem as a over x plus 1 plus b over x minus 1. And you go on like this, okay? So again, you multiply everything with, you can either guess here or you multiply everything with x plus 1, then set in x is equal to minus 1 and get the coefficient. So the rest is just the same. I just want to stress that for this function it's not really necessary, okay? Because if you check our table of the elementary integrals, okay, this is something like the inverse hyperbolic tangent or inverse hyperbolic cotangent. So actually here you can also check out your table and just write out the result here. You will get something which is in terms of ln absolute value of x plus 1 plus or minus ln of absolute value of x minus 1, and this is essentially the formula we deduced in one of the exercises for the inverse tangent, hyperbolic tangent. Okay, but the method is here the same. You can either use the method of integrating rational functions by writing it as a sum of partial fractions, or you just look in your, if you in our textbook at the very end you find a table of integrals and you see that actually this integral 1 over x squared minus 1 is standard integral. So you do not necessarily have to go through this procedure here for this integral. Okay, so this is the first case. Now second case. Again, we assume that q of x can be written as a product of only linear polynomials, so no irreducible quadratic polynomials do occur, but now some of the linear polynomials are repeated. So for instance, you have this r times some remainder. Okay, and in this case, you have to look at okay, how many times. And now for this guy, okay, you add in your in the expression where you set up f of x. So you have f of x is equal to. Now you have to look at every linear factor, and you have to check out, okay, how often does the linear factor occur. Now for this one, if it is r times, you have a1 over ax plus b plus a2 over ax plus b squared plus and so on plus to the r, okay, plus something which corresponds here with r of x. Okay, if you have a linear term which occurs r times, okay, for this linear term, okay, you have to write already so many terms. Okay. It's not just, for this linear term, you are not just if you just write AR over AX plus B over R, it won't be possible necessarily to solve for the coefficients. Okay, so actually you see something which you have to prove for this method as well is that whenever you do this, okay, I claim that whenever you set up a problem like this here, you get a solution. Okay, so you can really find coefficients such that you can write f of x in this form. This is something you have to prove actually. Okay, but if you have something like this here, you have to use so many terms. Okay, and for the remainder here, the same. Okay. So for instance, an example for this case is the following one. Okay, so this one, 3x squared minus x minus 3 over x plus 1 square, no square, x squared. Okay, so this one. So you see that, again, we have 3 steps. The first step is checking whether the given rational function is proper or improper. You see that the degree of the numerator is 2, the degree of the denominator is 3. So indeed, this rational function is proper. So this first step. So we do not have to do long division. Now, in the second step, we have to factorize the denominator. This is already done here. And we see that we are actually in the second case, because we see that there is one linear factor, namely x, which occurs twice. Okay. So we know that we have to set up the problem 3x squared minus x minus 3 over x plus 1 x squared is equal to. So for this one, we have to choose a, or let's first look at this one. So for this one, we already know from the first case, it's just a over x plus 1. And for this one, we have to choose b over x plus c over x squared. Okay. Don't forget that you have to choose 2 of them. Okay. Now, the task is again to compute a, b, and c. So again, you have 2 methods. One method is multiplying everything with x squared times x plus 1, and then comparing coefficients. This would be one method. The second method is choosing values for x. Now, for the first case, we saw that choosing values for x is much more successful. Here, it's a little bit more tricky to choose good values. So the troublemaker is this one here. Okay, so if you look at this one, we can use the method from before. We multiply everything with x plus 1 and choose x is equal to minus 1. Then this guy and this guy disappears. Okay, so a is easy to compute. Okay, so for a you have just to plug in here minus 1. So you have 3, 4, 1 over 1. So 1. Now, if you try to do the same here, you multiply everything with x, you will have a problem because okay, here you have an x, so this guy would disappear. But here you have still c over x, so you can plug in x is equal to 0. But if you multiply everything with x squared, okay, this works, of course. Because if you multiply everything with x squared, you have here an x, b times x, and here you have a times x squared. If you plug in x is equal to 0, this guy will disappear, this guy will disappear. So c can also be immediately computed. Okay, so c is equal to minus 3. Okay, and this is normally in general the rule is that you can always find the coefficient. You can easily find using the method I just showed you, multiplying and plugging in values. You can always find the coefficient which corresponds here to the highest power. Okay, so for this one it's always possible. So we have now already 2 now. In order to find the last one, we just choose any value of x. Okay, so for instance, x is equal to 1. Okay, so for this one, we have here 2 minus 1 over 2 is equal to. Now, a we have already, so we have here 1/2 plus b we do not have yet, plus and for c we have minus 3. Okay, so this will give you b is equal to minus 2. Okay, so the rule is in order to solve something like this here, okay, you have to, of course, it would be always possible, okay, to multiply everything with x squared times x plus 1 and compare coefficients. You would get a system of equations with 3 unknowns, okay, three equations with the 3 unknowns a, b, c. But the rule here is you can make life as easy as possible by intelligently choosing values for x. And then this kind of computation can be much shortened, okay, to the systematic method where you just use where you just compare coefficients of polynomials. Okay, so we have found that this can be written as 1 over x plus 1 plus, now b is 2 over x minus 3 over x squared. Okay, so the integral can now be easily computed. Okay, so the integral of f of x dx is now just the sum over those integrals. So the integral dx over x plus 1 plus 2 times the integral dx over x plus or minus 3 times the integral dx over x squared. Okay, and now the task of integration is very easy. So the first one is the ln of the absolute value of x plus 1 plus 2 times the ln of the absolute value of x plus 3 over x plus a constant. Okay. Okay, so this was the second case. Now, how about if you, if in the factorization of q of x you have irreducible quadratic polynomials? So this is the case 3. Or first, let me just mention how to set up the problem. So if q of x is equal to, so in this case you have, you also have irreducible quadratic terms, okay? But we assume that in this case the irreducible quadratic terms are all different, okay, are not repeated, okay? So the more easier situation corresponding to case 1, okay, so where b squared minus 4ac is smaller than 0 and a of x squared plus b of x plus c occurs only once. Okay, so for such a term, what you have to do is when you set up the problem, you have to set it up as now the numerator is not constant anymore, but a linear polynomial over ax squared plus bx plus c. Okay, so in this case, you have to set up the problem using such a partial fraction. First of all, I have to check whether the rational function is proper or improper. This one is proper, so I do not have to do long division. Now, as for the second step, I have to factorize the denominator. So in this case, I can write it as x times x squared plus 1. And this polynomial is irreducible. It's an irreducible quadratic polynomial. Okay, so we are really in this case here. So we know that we have to set up the problem as, okay, for this one, it's just the usual rule for a linear polynomial. So a over x. And for this one, this new rule here, plus bx plus c over x squared plus 1. Okay, so and again we have to find the coefficients a, b, and c. Now, as for x, you can use the usual method. You multiply everything with x and set in x and plug in x is equal to 0. So then you get immediately a. Okay, so a is equal to minus 1. So we know already that x minus 1 over x squared plus 1 is equal to minus 1 over x plus bx plus c over x squared plus 1. Okay, and once you know this here, okay, now you have several ways to find b and c. You can plug in other values for x and get two equations of two unknown b and c and solve this system of linear equations, or you multiply everything with x times x squared plus 1 and compare coefficients. But of course, the most easiest thing is you rewrite this as bx plus c over x squared plus 1 is equal to, so you push this on the other side, so you have x minus 1 over x squared plus 1 plus 1 over x. So here you can find common denominator. So you have here x minus 1 plus, okay. Because you have to multiply everything with x, you have still here an x, so I was just confused. So you have here x squared plus 1. Now you multiply everything with x times x squared, and you get easily. And you see already what the result here is. So you have here p x squared plus cx is equal to. So you see also here, as it must be, okay, the minus 1. Otherwise, there would be no b and c. So this is not a coincidence that here the minus 1 cancels out, because I claim that whenever you set up a problem like this, you will find a, b, and c. Okay, I claim this. We haven't proved it, but I claim this. So this here is not a coincidence. Or this must always happen. So you have this is x squared plus x, and now from comparing coefficients, you see that b is equal to c is equal to 1. Okay, so our original polynomial x minus 1 over x squared plus 1 is equal to minus 1 over x plus x plus 1 over x squared plus 1. And this you can write as minus 1 over x. So for this part, you cannot further simplify it in terms of you cannot write this as a sum of more simpler partial fractions. But this is already simple enough here, so you can write this for the integral like this here, plus 1 over x squared plus 1. And now computing the integral is very easy. So you have the integral over f of x dx is equal to, so for this one you get minus ln absolute value of x, plus, now for this one you can use substitution, okay, so because you see that the derivative here of the denominator is more or less a factor, so you have here 1/2 ln of the absolute value of x squared plus 1, and this one here is a standard integral, so this is the arctangent of x plus a constant. Actually, here you can remove the absolute value. Okay, so also this case is not so complicated to handle. And what you see here, whenever you have an irreducible quadratic factor, you will end up with something like this here. And you have to know, in order that the method works, you have to know how to integrate this. Now, in order to integrate this, you can always use the same method. You always write it as such a sum. For the first part, you always use substitution. Second part is always something in terms of tangent. Okay, so if you have something more complicated, maybe let's just look at something more complicated to make this point clear. If you have to compute this integral here, okay, so we have a proper rational function. The second step, so in the first step we have to do nothing, no long division. Now for the second step, okay, we have to try to factorize the denominator. But you observe that b squared minus 4ac, which is 4 minus 20, so minus 16 is smaller than 0. Okay, so actually this guy is already a irreducible quadratic polynomial. Okay, so we do not have to we do not have to use to set up the problem, we cannot simplify this by writing it as a term of partial fractions. Okay, which means we have directly, so this corresponds to one term in the partial fraction expansion, and we have directly to integrate it. But of course, such a term can always be handled similar to this situation, as I have just explained. The only thing you have to do is, okay, you first complete the square. Okay, so you have the integral over x plus 4. Now you complete the square, so you have x plus 1 square, plus 1, so you have here, so you have 4. Okay, so then you take out 1 over 4, so you have 1 over 4, and then you have the integral x plus 4, and here you have x plus 1 half square plus 1 dx. And now you substitute here. Then you get essentially what you have seen before. So you substitute u is equal to x plus 1 half, which means that du is equal to 1 half dx. So what you have is, this is equal to 1 over 4. We have to plug in here x is equal to 2u minus 1. So you have the integral here 2u minus plus 3 over, and this here becomes u square plus 1, and we have a 2 here, so here is 1 half du. Okay, and now in order to integrate it, you just use the same method as I have just explained. So this here is equal to the integral u over u square plus 1 du plus 3 half integral du over u square plus 1, and this is ln of okay, let's write it. This is ln of absolute value of u square plus 1 and 1 half in front of it, plus and this is a 3 half the arctangent of u plus a constant, and then you have to plug in for u this again. Okay, so this one goes then here and here. Okay, so you see that whenever you encounter in general such a rational function where the denominator is an irreducible quadratic polynomial, okay, we know how to. So this is essentially some ln plus, as you see here, plus some arctangent. Okay, so all such terms we can handle. Okay, now we are left with the last situation, which is the most general case where we have irreducible quadratic factors which occur more than once. Okay, maybe let's first discuss the situation, and then I show you an example. So case 4. In case 4, you have q of x is equal to a of x squared plus bx plus c to the r times r of x. Okay, and again p squared minus 4ac smaller than 0, and in r of x you do not have a term of the form ax squared plus bx plus c. Now, in this case, you have to choose, when you set up the problem, you have to choose a1 plus a1x plus b1 over, here you have ax squared plus bx plus c plus and so on plus arx plus br over ax squared plus bx plus c to the r. Okay, so again, you have to, for such a term, for such a factor, you have to set up r terms, okay, and then solve for all the coefficients. Okay, and this is the most general case. So the most general case is you look at every irreducible quadratic factor, you check out how often does this term occur in the factorization of q of x, and if it is r times, you need r terms in setting up the problem. Okay, so the first step is checking whether this rational function is proper or improper. This obviously is a proper rational function, so we do not have to do long division. Now for the second step, we have to find the factorization of the denominator, but it's already here, so we can skip the second step as well. And for the third step, we see that, okay, we have one irreducible quadratic factor, but which occurs twice, and we have one linear factor. So we have to set up the problem as 1 over x squared plus 1 square x is equal to, now, a over x plus b over, bx plus c over x squared plus 1 plus dx plus e over x squared plus 1 square. So maybe for this one I will, because it's the last example, so I will use the most systematic method, namely multiplying everything with the common denominator and then comparing coefficients. So you get here 1 is equal to, now, so for this one you have a times x to the 4 plus x plus 2 x squared plus 1 plus, now you have bx plus c times x squared, let's already write this as x to the cube plus x plus, and then you have dx plus e times x. Okay, so I multiplied everything with x times x squared plus 1 to the cube. Now I collect coefficients, so you see that the highest power which occurs here is x to the 4. Okay, so for x to the 4, you see that you have this one, and you have here one multiplying those two, so you have a b, so you have a plus b is equal to, and here the coefficient is 0, so 0. So this is the first one. Now for x to the cube, okay, so here you do not have an x to the cube. Here you get an x to the cube, which has a c, so c must be equal to 0 for x squared. Now here you have 2a. Now here you have a b, and here you have a d, which is 0 as well. And for x, you have here you have a c plus e is equal to 0. And the last one is for 1. So for 1, you have here a, and a must be equal to 1. Okay, so for instance, you see here that from here you see then that b must be equal to minus 1. So here we have already a, here we have already b, we have already c. So e must be equal to 0 as well. So this gives us e. Now the only one which is left is d. So here you have 2a, so 2, 1, d is minus 1. So d is equal to minus 1. Okay. So you see, it's not too complicated. But fortunately, this polynomial was very easy. If this polynomial is more complicated, then you get maybe a more complicated system of linear equations, which you can give Maple if it is too complicated. Maple can compute this very quickly. Okay, so no, I shouldn't have erased this. So our polynomial, so our rational function can be written as 1 over x plus, then we have bx plus c, so minus x over x squared plus 1, and then plus dx plus e, so minus x over x squared plus 1 square. And the integral here is easy to compute. So the integral is the ln of the absolute value of x for this term. Then for this term, you use substitution. So what you get is 1/2 ln absolute value of x plus 1. So actually, you can drop here the absolute value. Okay, and for this term, you get something similar. So plus 1 over x squared plus 1. And you have a 1/2 here, plus a constant. Okay, you see, we have been somehow lucky here that so if the a b c, if the c is not equal to 0, okay, it's not a problem, because then we have another term here which is essentially c over x squared plus 1, which gives an arctangent. But if b c d e, if the e is not equal to 0, okay, so if we have something like, so you see, we have been somehow lucky here. So for instance, if the last term is would turn to be out, let's say, minus x plus 1 over x squared plus 1 square, okay, which is possible, okay, by the way we set up the problem, then you will have to integrate this one. Okay. Now the first part is easy, because we see already here how to do it using a substitution. So the first part is 1 over 2 x squared plus 1. But you have still this one left. 1 over okay, who can tell me how to integrate this one? Because our method, if we are not able to integrate something like this here, our method does not work in general. Because in general, we will have to handle such terms here, even with a higher power here for 2. Okay, so in general, we will have to know, we certainly have to, we should know how to compute such integrals. Okay, this is what we in general need. Okay, this one corresponds to, if you look at the way we set up the problem to the r, this one corresponds more or less, if you forget about, this term is easy, or some part, okay, is, because it's just the inner derivative of this one, okay, so you can reduce this term actually, so, but you have to handle such a term, okay, and if you do some transformation, you will end up with this term here. So you can tell me how to integrate this one. It's the last problem which is left. If we can integrate this, we can integrate all rational functions. Okay, so who knows how to, you just have to tell me the method, not the result. Who knows, who has an idea? Yeah, right, yes, we discussed actually this case last time. Very good. This case we discussed already last time, okay? Because this is the usual trigonometric substitution. And using this here, this will reduce to some integral over trigonometric functions, which we have discussed also last time. Okay, so also for this case, for the general case, you can try to work it out. You can easily use this substitution here. Okay, and with this remark, we can integrate. We are able to handle all all rational functions. So whenever we have given a rational function, the task of integration is very easy, because we have a clear procedure how to do it, namely follow those 3 steps, and that's it. Okay. So first, check whether the rational function is proper or improper. If it is improper, use long division in order to write it as a polynomial plus a proper rational function. And for the proper one, look at the denominator, factorize the denominator, and set up the problem, as I have explained. Once you have set up the problem, you have to find all coefficients. You can do this systematically by multiplying everything with the common denominator and comparing coefficients and getting a system of linear equations, solving it, and then integrate. And for the integration, we saw that the most complicated parts are this one, okay, but for this one, we have last time learned the method. So this means we can compute all rational functions. I show you maybe one more complicated example just to summarize how to set up. if you have something like this here, just to see how to set up the problem in general. So you see this is already a proper rational function. Okay, so we do not have to use long division. Now we also already have the factorization of the denominator. So the only thing which is left is to set up the problem and I should also remark that this polynomial here is irreducible quadratic. This as well, as you see easily. Okay, and in order to set up the problem, what you have to do is, okay, for this one, you need 3 terms. Okay, a over x plus b over x squared plus c over x to the cube. For this one, you need 1 plus d over x plus 1. For this one, you only need 1 because this irreducible quadratic polynomial occurs just once. So you have ex plus f over x squared plus x plus 4 plus. Then you have this one which occurs twice, so you need 2 terms. Gx plus h over x squared plus 3 plus ix plus j over x squared plus 3 square. Okay, and then you have to find a, b, c, d, e, f, g, h, I, j. Okay, so you multiply everything with this common denominator and compare coefficients. You will get a system of equations with 10 equations and 10 unknowns. You solve it, you plug everything in, and you integrate. So this is easy to integrate. This is easy to integrate. This is easy to integrate. This one is easy to integrate. This one is you first complete the square, and then it's more or less. This is more or less ln of something of a quadratic polynomial plus something arctangent. This one is also easy. This is the same as this one, and this one you have to use x is equal to. So more or less for this one you have to use x is equal to tangent. Tangent of theta, this substitution in order to compute the integral, but it becomes solvable. Okay, so no matter how complicated the rational function looks like, we can solve it. I'm not going to solve this. Okay? Maybe it's possible to solve some integral much more easier. Okay, for instance, if you have something like of course, don't use this method, okay? Because you can do an easy substitution here, okay? For the method, you would have to factorize this one, which gives you many, many terms. Then you have an even longer expression here, okay? So for something like this here, do not use the method, okay? But it would be possible by using the method. If you so this one, I think Maple can do rather quickly because here Maple still knows the trick, but maybe one which is even more tricky is this one. Okay, so for this one, one possibility again would be using the method. You see, this is a proper rational function. Now you factorize the denominator, which gives you many, many terms, and then you set up the problem and solve it. Okay, this would be one problem. This would be one method, but it's more easier here to figure out the following substitution. So you can take out the x. Okay. Now you see that if you substitute u is equal to x to the 99, okay, then you see that du is equal to 99x to the 98 dx, and you are lucky, okay, because you see this is 1 over 99. This one here becomes u minus 1. This one becomes du, and if you divide this here, you see that this x times this one is again u. Okay, so you are lucky. Okay, and this is much more easier than the original one. And now you can apply the method in order to solve this one, which is much more easier. So sometimes it pays off to think a little bit. Okay, if you give this example Maple, okay, Maple will need a long time to come up with the answer, because Maple is just stupidly using the method which I just introduced. Okay, Maple is not able to come up with this trick here. Okay, so sometimes whenever you have given a rational function, okay, the first step is to think whether there is an easy method to solve it. If there is no easy way, so first you should spend a few minutes to think whether there is an easy method. If there is no easy way, you just use the procedure. Okay, and this is of course also easy. It's just lengthy in some cases. So this is one thing. The last thing I want to mention is that sometimes integrals, okay, can be easily transformed into, because we now already know that whenever we have a rational function, whenever we have to solve an integral of a rational function, we can solve it. Okay, so this is an advantage, because if we have given any integral, okay, we can, one general principle would be try to find a substitution such that the integral is becoming an integral of a rational function. Then you can solve it. Okay, and so this would be a general tool. Okay, so this is what our textbook calls rational substitutions, and there are several examples where this really works out. For instance, quite often, if there are roots involved, you can find a substitution which makes the problem rational. Another typical example is this one. So e to the 2x over e to the 2x plus 3 e to the x plus 2 dx. Okay, so you see in this case, the obvious substitution is u is equal to e to the x. Okay, so du is then equal to u dx. Okay, and now if you do this substitution, what you get is the integral of u square over, here you have u square plus 3u plus 2, and you have dx is du over u, so you have this integral here. And this here is we can solve it using the method I just explained. Okay, so this is now a general principle. Okay, whenever you have an integral and you find the substitution such that the integrand is getting a rational function, okay, you are done, because the rest is just using a standard procedure. The rest should go without thinking. This is what I mean by standard procedure. Okay, something you can tell the computer, and the computer can do it stupidly. And in our textbook, you see some examples, some other examples. It's quite frequent if you have here something where roots are involved. You can quite frequently find it, because if you have something like the square root of x, for instance, you can choose u is equal to the square root of x, and you can transform it like this quite often, or in most of the cases, to a rational function. I'm not going to show you an example. You can look at the example in our textbook, and there are more examples in the part where you find the exercises. Okay, so we have discussed now a couple of classes of functions which we are able to integrate. The problem, the reason why we have to use an approach like this is, as I have explained, that there is no good way how to compute the integral of a product. Okay, so whenever you have a product, you can just use the integration by parts, but you will end up with another integral. Okay, so this makes integration normally more complicated than differentiation, where you do not encounter this problem. So what we have done in section, or what our textbook is doing in section 7.2, 7.3, 7.4, is just discussing classes of functions where you have general principles. Like we saw trigonometric functions, we can handle most of them systematically. Also, by using the trick of trigonometric substitution, we can handle quite a lot of integrals. And this is another class of functions, rational functions, which are completely manageable. Now, you find in our textbook some more chapters which explain general strategies of integration and so on, but I'm not going into details. I should maybe mention that another reason why the task of integration is much more complicated, I have already explained this before, but another another reason why the task of integration is much more complicated than the task of differentiation is that you encounter something which is not possible for differentiation. So for instance, if I ask you to come up with an expression for this integral here, now we know that if you want to have this integral, we know one solution, namely because this is just another symbol for the antiderivative, but we know that an antiderivative, for instance, is given by this function here. So if you define a function like this here, you will get an antiderivative. Okay, but so the question remains. Okay, is it possible to write this function here, f of u, in terms of the function you know? The functions you know are like hyperbolic, trigonometric functions, exponential functions, logarithm, and also hyperbolic functions. Okay. So the question is, are you able to write this here in terms of the function you know? And there is a deep theory in mathematics which tells you, no, this is not possible. So it's not possible to write this in terms of the functions you know. Okay, and this is something you do not have for differentiation. For differentiation, given a function, an expression for a function, you can find the derivative. Okay, you have rules, you can find the derivative. But for integration, there are certain integrals. So whenever you are faced computing an integral, okay, it might be possible that there is no answer. Okay, so there's always this possibility, and so there is always an uncertainty in the problem. So maybe it's not solvable. Okay, or not solvable means that maybe you cannot write it down in terms of the functions you know. And this is another reason why integration is more complicated than differentiation. Actually, if you give something like this here, maple, I should maybe say this. Okay. If you give this maple, maple can solve it. But the reason why maple can solve it is because maple know more functions than you know. Okay. You essentially just know trigonometric functions, hyperbolic functions, and logarithmic functions, exponential functions. But maple knows much more. If you know much more functions, of course it's possible to write this out. Like the most easiest way is you define this as a new function. Okay, then maple can solve it because it just writes the name of this function. Okay, this is something we do also frequently in mathematics. So this function is very important in probability theory. So this function, or using maybe with a different norming and so on, has a name in mathematics. So this is a function which is well known. And if you know the name of the function, you can, of course, you write is equal to the name of the function. There is even but this is something which you are not going to learn even in unless you choose you are going to choose very deep courses on mathematics. There is even an algorithm deciding for a given function either whether the function is expressible in terms of the function in the functions you know, then giving the answer, or if it is not possible, saying no, it's not possible to express it in terms of the function you know. So there's a standard method, actually, an algorithm which solves this problem completely. And Maple normally has implemented this algorithm. So in many cases, if Maple tells you there is no answer, then this doesn't mean Maple cannot find it. This means it's not possible to express this integral in terms of the functions you know. So this problem, actually, from a mathematical point of view, is completely solved. But you need much more to know much more about mathematics to understand this. Okay. Now, actually, this is everything I wanted to say about integration techniques. What we still want to do in Chapter 7 is to extend the notation of integration to so-called, this is something you also have frequently in applications, so-called improper integrals. It's like integrals which are not proper. What we have discussed so far, proper integrals. Now, improper integrals, there are two types. The first type is like you have, so these are definite integrals. The first type is one of the limits, upper or lower limits, is infinity or minus infinity. Okay, so infinite integrals. Now, so for instance, the problem is as follows. So assume we have given this function here, 1 over x squared. Now, if we go back to the area problem, so this is the function 1 over x squared. This here is 1. So if we go back to the area problem, okay, we could ask the question, okay, is there an area below the function above the x-axis, okay, but where you do not restrict the range, okay, so from 1 to infinity. Or in other words, actually the question is not whether there is an area or not. The question is to define the area. Okay, so how to define this area in a sense that your definition is useful or makes sense. Okay, so how to define the area? This is actually our question. Now you see that one way to approach this problem is you fix here some t. Okay, you see that actually you can easily compute the area from 1 to t. So this we call a of t. So this is the area below the function and above the x-axis from 1 to t of dx over x squared. Now you see this can be easily computed. So you have 1 minus 1 over t. And now you observe that as t is getting very large, okay, this a of t, so the area as t is moving, this limit here exists. So the limit of a of t as t tends to infinity exists and is equal to 1. Okay, so this is something you observe. And because of this observation, okay, it obviously makes sense to say the area here is defined and is equal to 1. So we will define such an area, okay, as a limit of areas. Okay, or in general, we will so this is for the area, and for the integral, we will define the integral from 1 to infinity as the limit of integrals. Okay, so we will define the integral from 1 to infinity of dx over x squared as the limit as t tends to infinity of these integrals here. So whenever this limit here exists, we will say that this integral here exists or is convergent, and the value is equal to 1. If this limit does not exist, we will say this integral is divergent. Okay, and this is a so-called improper integral of first type. Okay, similarly, you can define an improper integral of improper integral for the case where your lower limits, so not for 1 to infinity, but for instance minus infinity to 0. Okay, similar. You have given a function which is continuous from minus infinity to 0. Okay, you look at the integral from minus t to 0 and check whether the limit exists or not as t tends to infinity. If the limit exists, we say that the integral converges or exists is equal to the limit. If the limit does not exist, we say that the integral is divergent. And finally, an integral from minus infinity to infinity. Okay, for this case, we write this integral. Maybe I should write this down. So finally, for this situation, of course, what we need is f of x is continuous on R. So this is what we need. In this case, okay, we write the integral as the integral from minus infinity to a f of x dx plus the integral from a to infinity of f of x dx. Okay, and if both integrals are convergent, okay, for some a, if both integrals are convergent, we will say this integral is convergent and is equal to this sum here. If one of those two is divergent, this integral is already divergent. Okay. So this is the general definition. And of course, if you define something like this here, what you have to prove, strictly speaking, what you have to prove first is that this definition does not depend on the choice of a. Okay. Because we say here for some a, if you write it, if you have this integral, okay, you look at those two integrals for some a. If both of them are convergent, okay, then this integral is called convergent. Okay, so you have to prove, the first thing you have to prove is this is independent of the choice of a. Okay, you find an exercise in our textbook which proves this, or which asks you to prove this. So this is a infinite integral where both lower and upper limit are infinity. Okay. So maybe let's check out some example. So we saw already 1 over x squared. Okay, so how about this integral here? Okay, so by definition, what we have to check is whether the limit as t tends to infinity, the integral from 1 to t dx over x exists. Now this we can solve, so we have the limit t tends to infinity. Now we have ln of t, but as t tends to infinity, this will tend to infinity. Okay, so this integral is divergent, does not exist. Okay, so you see that for the function 1 over x squared, the integral, the improper integral exists. For 1 over x, the improper integral does not exist. So essentially, this somehow depends on the speed with which the function tends to 0. Okay, if the function tends to 0 fast enough, if the function doesn't tend to 0, there will be no area. Okay, clearly. But if the function tends to 0 fast enough, there will be an area. But if the like this here, 1 over x also tends to 0, but not fast enough, so there will not exist an area here. You see from this also something interesting is that if you look at the function 1 over x, there is no area here. Okay, but if you rotate it about the x-axis, okay, then if you use, for instance, the method of cross sections to compute the volume of the solid you obtain by rotating this area about the x-axis, okay, then you have pi times the integral from 1 to infinity dx over x squared, which exists. Okay, so you see that 1 over x, this function, this area does not exist. But if you rotate this area about the x-axis, the volume exists. So you see, you have something like some strange effects. Okay, some strange phenomena. Okay, for this kind of area definitions. Okay, so this is one example. Now, a more general example is, okay, to check out, okay, what happens if you choose 1 over x to the p, where p is any real number. So let's check out this one. Okay, so let's check out this integral from 1 to infinity dx over x to the p. We saw already p is equal to 1 divergent, p is equal to 2 convergent. Now, how about the general case? So you see, by definition, this is the limit as t tends to infinity. Then the integral from 1 to t dx over x to the p. Now, this integral is easy to compute. So you have x to the minus p plus 1 over minus p plus 1. So this actually, this is the case where p is not equal to 1. But p is equal to 1 we have already discussed, evaluated at 1 and t. So what you get is the limit as t tends to infinity. Now, for the upper limit, or let's write this as 1 over p minus 1 minus 1 over p minus 1, t to the p, okay, this one. 1p, 1, okay, this is correct. Now, you see, as t tends to infinity, what you need is that p is larger than 0, that this limit here exists. Otherwise, this limit tends to infinity. So you see that if p is larger than 1, then this integral is convergent. So actually, we can even write down the value, which is 1 over p minus 1. And if p is smaller than 1, this integral divergent. Okay. So you see that, and in this case, the limit would be infinity. Okay, so you can say that in some sense, so this integral would be equal to infinity. Okay. Now, we will see next time that actually if you know this here, okay, you can already, for quite a lot of integrals, just by looking at them, you can already check out whether they will converge or not. Okay, because this just tells you that if p is larger than 1, okay, then the speed with which this function here, f of x, is equal to 1 over x to the p, as x tends to infinity, approaches 0, is fast enough to make the area exist. But if p is smaller or equal than 1, then this function does not tend to 0 fast enough. Okay. Of course, the case where p is equal to 0 or p is even negative. Okay. In this case, of course, the area cannot exist because the function is, if p is smaller than 0, this function is increasing. Okay. So there is no way that the area exists. Okay. Just by looking at the area would be clearly infinite. Okay. So you see that so p is equal to 1 is kind of the so actually p is equal to 1 is the critical number. If p is larger than 1, this function tends to 0 fast enough such that the area exists. Okay, so, and next time we will look at some more examples and also exploit this kind of behavior in order to understand quickly whether other given improper integrals are convergent or not.